Come on, my dears, let us proceed further in chapter number 8. Today's first article is really very interesting, and in the textbook they have not given the discussion in the proper length. They have just finished that article very shortly. I would like to explain you very much in detail. I just appeal everybody to pay nice attention on the board. Okay, please. What is the title? Look. Stationary waves in pipe. If an instrument is made up of pipe, then inside that pipe it is having some air column, right? Then using the vibrations in that air column, if some pleasant sound is produced, it is called musical note, and all the musicians whichever use such instruments, they are called wind instruments. Such instruments are called wind instruments, in which the air is to be blown and then after the vibrations are set up with proper frequency. Such instruments involve some sort of pipe, but such pipes are found to be of two different types. One is that in which one end is open, another end is closed. Such a pipe is called closed pipe. Closed pipe. Here it is. Closed pipe. There are two examples for closed pipe. Remember, clarinet and trumpet. Clarinet and trumpet. Okay. Now in textbook they have given such names, clarinet and trumpet. But actually how are these instruments? That they have not shown. Okay. I have got one very good dictionary called Visual Dictionary, in which photographs are given for these instruments. I would like to show those photographs to you also. Please look here carefully. First of all, I am showing you trumpet. Trumpet is having such a shape. Look. The bottommost photograph on the left side of this page, it is trumpet. Look at it carefully. Okay. Now I am showing you clarinet. Clarinet is such a pipe. Here also, bottommost photograph on the left side, it is clarinet. Correct? Fine. Now another pipe is such a pipe in which both the ends are open. We would call it open pipe. Open pipe. Open pipe. Correct? Example is flute. Flute is an example of an open pipe. Everybody has seen this flute. Okay? So I am not showing you that flute in the photograph. Got it? Let us see how sound is produced by process of called resonance in the air column in this pipe. How are they produced? I am showing you. Let us discuss the things first of all for closed pipe. Consider this as a closed pipe whose one end is closed, another end is open. Suppose that pipe has length capital L. Now, suppose you take a tuning fork having its frequency equal to V upon 4L. How I am going to get this expression? I will show you. Correct? Wait for a minute. V upon 4 into L. What is V? Velocity of sound in this pipe, in the air column in the pipe, and L is the length of the pipe. Just consider a tuning fork having its natural frequency equal to V upon 4L. Okay? Then strike that tuning fork with rubber pad and just hold it just above this closed pipe. Here. This sponges will start vibrating with this much frequency. At that time, every air particle inside this air column, inside the pipe, also starts vibrating with the same frequency. Okay, fine. Now tell me, here when all the air particles are vibrating, in this case it so happens that amplitude of oscillation for particle located at this very position is found to be maximum. That's why that point is called antinodal point, antinode. That's why I am putting capital A, correct? And as you come down, as you go deeper and deeper inside the closed pipe, it so happens that amplitude of oscillation of air particle goes on decreasing. Finally, for this very air particle, just in the contact with bottom closed end, its amplitude is 0. That's why that point is called nodal point or node, shown by symbol N. Correct? Fine. So what I mean to say, here amplitude is maximum, and as you come down, amplitude goes on decreasing, and here amplitude becomes 0. But how to show the same fact in the figure? Then you know, everywhere in all the reference books, in our textbook also, what have they shown is not actually wave pattern which is produced here. They have shown equivalent wave pattern produced in a string. You know, in a string there are transverse waves. There are transverse waves. In a string, what will happen? The direction of oscillation of particle and direction of propagation of wave, both of them are perpendicular. That's why it is called transverse waves. But here which wave is propagating? Sound wave. For a sound wave, you know, they are longitudinal waves, and in fact all the air particles, they just oscillate this way. During condensation and rarefaction, they oscillate this way, correct? And when the direction of propagation of wave is this, direction of oscillation of particles is parallel to that, so the waves propagating right now, they are longitudinal waves, correct? But just we wanted to show that fact that here amplitude is maximum, and as you come down, amplitude goes on decreasing. Finally, amplitude becomes 0. Here, just we have shown here equivalent stationary wave pattern produced in the case of a string, okay, where you can expect transverse waves, correct? But after watching this figure, please don't be misguided that sound waves are transverse waves. No, sound waves are not transverse waves. Sound waves are longitudinal only. Please be careful. Now come on. How are these stationary waves produced? I am showing you. When this sponge will vibrate downwards very first time, at that time, very first sound wave generated would propagate this way. Look here, this way. Fine. It is made incident here, and after that it will be getting reflected. But by the time from here, second sound wave has already been generated, and that second sound wave has already started propagating downwards this way. So inside this pipe, there will be superposition between first wave which is traveling vertically upwards and the second wave which is traveling vertically downwards. So there will be superposition, correct? And because of superposition of these two waves propagating towards each other, there are stationary waves set up in this air column, in which the amplitude of oscillation of particle located at this position is found to be maximum. That's why we call it antinodal point, and amplitude of oscillation of particle located at this position is found to be 0. That's why we call it nodal point, correct? And equivalent stationary wave pattern, if it is observed in case of a string, it would be found like this, correct? Fine. Now, you just do one thing, express L in terms of lambda. Express L in terms of lambda. Fine. You know distance between consecutive antinode and node. Last time in the theory we had studied distance between two consecutive antinode and node. How much it was? It was lambda by 4. Lambda by 4. So this much distance is lambda by 4, and the same distance is also giving you length of the pipe, correct? So L is right now lambda by 4. Correct? Now you do one thing, you take another tuning fork having frequency, natural frequency 3 times than this frequency, 3 times than this, that is 3 into f1, 3 into f1, correct? Why like that? I'll tell you, wait, just be patient. Just take a frequency 3 times than this frequency, and then after striking it with the rubber pad, hold it here. Then the stationary wave pattern observed inside is different than this. It is found to be like this. And in this stationary wave pattern, tell me, how much is this length? How much is this length? Don't you know distance between two consecutive antinode and node? It is lambda by 4. So this much distance is lambda by 4. Correct? Come on. This is also lambda by 4. This is also lambda by 4. So altogether from here to here, come on, lambda by 4 plus lambda by 4 plus lambda by 4. How much it is? 3 lambda by 4. Here it is. 3 lambda by 4. Correct? And now you take frequency of tuning fork 5 times than this frequency. 5 times f1. 5 times f1. Okay? And strike it with a rubber pad. Hold it here. At that time, in the same pipe, you will have stationary wave pattern like this, in which you know distance between two consecutive antinode and node, it is lambda by 4. You can see here 1, 2, 3, 4, 5. So this total length is 5 into lambda by 4. How much? 5 into lambda by 4. 5 into lambda by 4. Got it? Now tell me, these all values of L in terms of lambda, they are, come on, lambda by 4, 3 lambda by 4, 5 lambda by 4, after that, come on, 7 lambda by 4, 9 lambda by 4, got it? Dash, dash, dash. Such all values, if you want to express in a single term, that single term you can always write this way, L equals to 2n minus 1 into lambda by 4. L equals to 2n minus 1 into lambda by 4, where values of n you must change like this, 1, 2, 3, dash, dash, dash. If you are still not convinced, you can just verify. Put n equal to 1. Put n equal to 1, then you get L equals to lambda by 4. Here it is, lambda by 4. Correct? Put n equal to 2. 2 to the 4 minus 1, that is 3 lambda by 4. Here it is, 3 lambda by 4. Put n equal to 3. 2, 3 is 6 minus 1, 5 lambda by 4. Here it is, 5 lambda by 4. Got it? Fine. Now just find out lambda from here. It will be how much? Transfer this 4 here in the numerator. Transfer this 2n minus 1 in the denominator. So lambda would be 4 into L upon 2n minus 1. 4 into L upon 2n minus 1. Got it? But if you will change the value of n, then value of lambda will change. So different values of lambda we want to express using different symbol. That's why I am using n here as a suffix. Lambda n, you must write n well below lambda. Okay, like this, please. Lambda n equals to 4L upon 2n minus 1. Fine. Now, don't you know wave velocity, it is always product of frequency and wavelength. So, V equals to F lambda. Just write suffix n. Here you write Fn, here you write lambda n. The wave velocity for any frequency of wave here is same, because the waves are going to propagate in a given air medium. For a given medium, the wave velocity is constant. So this wave velocity is constant. Okay, the wave, this frequency will change, this wavelength also will change, like that. Now this Fn will be as it is. Now just put the value of lambda n. What is it? 4L upon 2n minus 1. 4L upon 2n minus 1. Correct? And now find out Fn from here. Find out, it is 2n minus 1 into V upon 4L. 2n minus 1 into V upon 4L. 2n minus 1 into V upon 4L. Correct? Now I am showing you how I got these frequency values. I am showing you now. Look. Put n equal to 1 here at both the places. Then you will get F1, it will be equal to 2 into 1, that is 2, minus 1, that is 1, 1 into V upon 4L, that is V upon 4L, here it is, V upon 4L, correct? Now this frequency, which is shown by symbol F1, is found to be smallest among all these frequencies. That smallest frequency, you know, it is called fundamental frequency. What is it called? Fundamental frequency. I written here, fundamental frequency, correct? It is also called first harmonic. First harmonic. Okay, fine. Now place n equal to 2 here. Place it. Then you get F2 equals to 2 2s are 4 minus 1, that is 3V upon 4L. Here it is, 3 into V upon 4L. Correct? And place n equal to 2 here, you will get F2 equals to 2 2s are 4 minus 1, that is 3 into F1. 3 into F1. Correct? Come on. That's why I had taken frequency 3 times and then F1. 3 times then F1. Got it? Now, this is the frequency which is higher than F1. We call it first overtone. Say first overtone. I have written here, first overtone. It is higher than F1, correct? And because that frequency is 3 times fundamental frequency, we call it third harmonic. Third harmonic. That's why written here, third harmonic. I repeat, because this frequency is 3 times fundamental frequency, we call it third harmonic, correct? And it is very first value possible which is higher than F1, then that possible frequency which is higher than F1 is called first overtone, correct? Immediately after F1, whichever higher frequency is possible is called first overtone. First overtone. Got it? Now place n equal to 3 here. F3 will be 3 2s are 6 minus 1, that is 5 into V upon 4L. 5 into V upon 4L. Put n equal to 3 here and here. Then you get F3 equals to 3 2s are 6 minus 1, that is 5 F1. 5 F1. 5 F1. Now tell me, because this frequency is 5 times fundamental frequency, 5 times fundamental frequency, we call it fifth harmonic. Fifth harmonic. I've written here, fifth harmonic. Okay? And it is the frequency which is higher than first overtone. Higher than first overtone. Higher than this is this, correct? Higher than first overtone, we will call it second overtone. We will call it second overtone. Here it is. Second overtone. Got it? What is F1? That is minimum frequency. We call it fundamental frequency or first harmonic. What is higher than that? It is 3F1. We call it third harmonic or first overtone. What is higher than that? 5F1, which is fifth harmonic or second overtone, and so on. Got it? Please remember, these all the things are possible in case of, come on, closed pipe. In case of closed pipe. And the last point to be noted here, n minus 1th overtone is equal to 2n minus 1th harmonic. N minus 1th overtone is equal to 2n minus 1th harmonic. Then you may have a question, how? I am showing you. Put n equal to 2. Put n equal to 2. 2 minus 1, that is 1. So it is first overtone. Here it is, first overtone. Correct? And put n equal to 2 here. 2 2s are 4 minus 1, that is 3. So it is third harmonic. Third harmonic. Here it is. Third harmonic. Put n equal to 3. 3 minus 1, that is 2. Second overtone. Here it is. Second overtone. Put n equal to 3 here. 3 2s are 6 minus 1, that is fifth harmonic. Fifth harmonic. Here it is. Fifth harmonic. Got it? These all things I have written and explained to you for closed pipe, remember. And now we go for open pipe. Open pipe. Okay. What was the example for open pipe? Flute. Okay. Consider an open pipe which is open at both the ends. Fine. Now inside this pipe we have some air column. Correct? The length of the pipe, as usual, we are taking capital L. Now tell me. Consider this much frequency. Why it is this much? I will tell you. Wait. Consider this frequency V upon 2L. And you just take a tuning fork having this much frequency as natural frequency. Correct? Strike that tuning fork with the rubber pad and hold it at the top end, at this just above the open pipe, at this top end, you just hold it. Correct? Then because of the vibrations of the sponges, here also air particles start vibrating with the same frequency. At that time, here we get stationary wave pattern as shown in the diagram, in which you can notice the particles situated at these two positions undergo vibrations with maximum amplitude. That's why I'm going to call it as antinodal point A, correct? This air particle starts oscillating with maximum amplitude here also. That's why these two positions are antinodes. And here is that position at which the particle does not oscillate at all. It remains at rest, means amplitude is 0. So it is called nodal point N, correct? Now tell me, how would you express L in terms of lambda? Very simple. Don't you know distance between consecutive antinode and node? How much it is? Lambda by 4. Distance between consecutive antinode and node, how much it is? Lambda by 4. So this much is lambda by 4. Again this much is lambda by 4. Lambda by 4 plus lambda by 4. How much it is? Lambda by 2. Here it is. Lambda by 2. Correct? So L equals to lambda by 2. Now you take frequency of tuning fork double than this. Double than this. So I am writing here 2F1. Correct? Strike it with a rubber pad. Hold it here. Then you will have such a stationary wave pattern inside the pipe. And in which you can see in the diagram, distance between consecutive antinode and node, how much it is? Lambda by 4. So this is lambda by 4 plus lambda by 4 plus lambda by 4 plus lambda by 4. So it is 4 into lambda by 4. 4 into lambda by 4. So it is lambda. That's why I am putting L equals to lambda. Got it? Fine. Take another tuning fork having frequency 3 times than this frequency. 3 times than this. So I am putting here 3F1. And if you strike with the rubber pad, and if you hold it here at the top end of this pipe, then you will have stationary wave pattern like this, in which the distance between consecutive antinode and node, you know it is lambda by 4. You can see now 1, 2, 3, 4, 5 and 6. 6 into lambda by 4. 6 into lambda by 4 means what? 3 lambda by 2. 3 lambda by 2. Here it is. L equals to 3 lambda by 2. Got it? Now tell me. So here, in case of open pipe, stationary wave patterns are produced inside the air column, which satisfy which condition? For that, the length of the tube should be equal to either, come on, lambda by 2, or it should be lambda, or it should be 3 lambda by 2, or it should be 2 lambda, or it should be 5 lambda by 2, and so on. Correct? Come on, lambda by 2, lambda, 3 lambda by 2, 2 lambda, 5 lambda by 2, dash, dash, dash. If you want to accommodate all these values in a single term, you can express the length of the open pipe this way. L equals to n lambda by 2. L equals to n lambda by 2. If you don't trust, then you can verify. Change the values of n like this. Look here, 1, 2, 3, dash, dash, dash. Put n equal to 1. Then L equals to lambda by 2. Here it is. Correct? Put n equal to 2 will cancel, L equals to lambda. Here it is. Put n equal to 3 lambda by 2. Here it is. 3 lambda by 2. Got it? Fine. Now find out lambda from here. Lambda should be how much? It should be 2L upon n. 2 into L upon n. But the way you will change the value of n, accordingly lambda also will change. So we want to show different values of lambda by different symbol. That's why we have given suffix n. So we write lambda n. Where you should write n? Well below lambda. Please take care while putting the symbols. Lambda n equals to 2L upon n. Now, don't you know, wave velocity is frequency multiplied by wavelength. So V equals to F into lambda. Here you write Fn, here you write lambda n. Fn as it is. What about lambda n? It is 2L upon n. 2 into L upon n. And now find out Fn. It will be n into V upon 2L. N into V upon 2L. Correct? And now tell me, put n equal to 1. Correct? Put n equal to 1. Then you get F1 equals to V upon 2L. F1 equals to V upon 2L. Correct? Now you got it? How I am getting the formula of F1? Just put n equal to 1, you will get V upon 2L. Correct? Among the possible frequencies here in case of open pipe, this is found to be the smallest. We call it fundamental frequency or first harmonic. Fundamental frequency or first harmonic. Got it? And then in place of V upon 12, we can write F1. In place of V upon 12, we can write F1. So it is N into F1, N into F1. Okay. Now place N equal to 2, here also and here also. Put N equal to 2, F2 will be 2 into V upon 2 into L, 2 will cancel, V upon L. F2 equals to V upon L. Put N equal to here, then you get 2F1, here it is, 2F1, correct? And because this frequency is double than fundamental frequency, 2 times fundamental frequency, we call it second harmonic. What do we call it? Second harmonic. And it is a frequency which is higher than first harmonic, we call it first overtone. First overtone, here it is, first overtone, correct? Now place N equal to 3, place it here and here, F3 equals to 3V upon 2L, F3 equals to 3V upon 2L, put N equal to 3 here, so it is 3F1, 3F1. Because this frequency is 3 times fundamental frequency, we call it third harmonic, here it is, third harmonic. But it is higher than first overtone, higher than first overtone, that's why we will call it second overtone. Don't you see this frequency is greater than this, correct? If any frequency which is possible and yet it is greater than first overtone, we must call it second overtone, second overtone. In this case, remember, nth overtone is equal to n plus 1th harmonic. Nth overtone is equal to n plus 1th harmonic. How? I am showing you. Put n equal to 1. So first overtone, here it is, first overtone should be equal to, look, put n equal to 1 here, 1 plus 1, that is 2, that is second harmonic, here it is, second harmonic. Put n equal to here, then second overtone, put n equal to here, 2 plus 1, third harmonic. Second overtone should be equal to third harmonic. Second overtone should be equal to third harmonic. Got it? These all things are applicable for stationary waves produced in open pipe. Example is flute, correct? Here we have discussed for closed pipe, here we have discussed for open pipe. And now let us discuss one very good extra question, not directly given in the textbook. Mention some points of differences between the stationary waves produced in closed pipe and stationary waves produced in open pipe. Let us see some points of difference now. Here I am writing stationary waves in closed pipe. Here I am writing stationary waves in open pipe. Okay, fine. First point. Here, in case of closed pipe, antinodal point is obtained always at one end, which is open end. Okay. Here, antinodal point are obtained at both the open ends. Okay. Here, one antinodal point is obtained at one open end, and here two antinodal points are always obtained at both the open ends. That's what I mentioned here. Come on, here antinode is obtained at open end and node is obtained at close end. Antinode at open end and node at close end. Okay. Here at both the open ends we get only antinodes. That's what I have written here. Here antinodes are obtained at both the open ends. Okay, fine. What about second point? Only odd orders of harmonics are possible. Odd orders of harmonics are possible. Which harmonics are possible here? Look, F1 is possible, then 3F1 is possible, then 5F1 is possible, F1 that is first, 3F1 that is third harmonic, 5F1 that is fifth harmonic, 7F1 seventh harmonic, 1, 3, 5, 7. What are these? Odd orders of harmonic, correct? Even orders of harmonic are not possible in case of closed pipe. Got it? And here F1 is also possible, 2F1 is also possible, 3F1 is also possible, 4F1 is possible, 5F1 is possible, dash, dash, dash. So here all the orders, whether odd or even, all the orders of harmonics are possible in case of open pipe. Okay, I written here. Here all orders of harmonics are possible. Then look, Here number of antinodes and nodes are equal. Number of antinodes and nodes are equal. How many number of antinodes here? 1. Then number of node is also 1. Number of antinodes 2. Number of nodes is also 2. Number of antinodes 1, 2, 3. Number of nodes is also 1, 2, 3. So in case of stationary waves in closed pipe, number of nodes and antinodes are equal. And here, come on, number of antinodes is 2, then number of node is 1. If number of antinodes is 3, then number of nodes is 2. If number of antinodes is 1, 2, 3, 4, then number of nodes is 1, 2, 3. So what do you notice here? The number of antinodes is greater than number of nodes by 1. Number of antinodes is greater than number of nodes by 1. I written here. Here number of antinodes is greater than number of nodes by 1. Fine. Then fourth point, for example, stationary sound waves produced in clarinet. Example of closed pipe, I already told you it is clarinet or trumpet. And here it is flute. Example, come on, stationary sound waves produced in flute. Okay. And last point, what was the fundamental or minimum frequency possible here in case of closed pipe? It was V upon 4L. Correct? And here it is V upon 2L. V upon 2L. Here fundamental frequency is V upon 4L. Here fundamental frequency is V upon 2L. This frequency is double than this. If you are talking about same length of the pipe, whether it is closed or open, then L is same, and because air medium is also same, then wave velocity V also is same. In that case, this frequency is double than this. If you multiply this by 2, you will get this frequency, correct? So in case of open pipe, the frequency is greater, means particles are oscillating with higher frequency, okay, in case of open pipe, remember. My dears, in the previous figures for stationary waves produced in closed pipe and in open pipe, have you noticed one thing? As frequency increases, wavelength decreases. How? All the stationary waves are produced in the same air medium where velocity is constant. V equals to F lambda equals to constant. When F into lambda is constant, naturally when frequency will increase, come on, wavelength will decrease. And when wavelength will decrease, then crest and trough would come closer. So in the previous figures, you must have noticed that as frequency increases, the crest and trough are coming closer, thereby wavelength is said to be decreasing. Simple, fine. Now, based upon those two topics, we have got example number 16 in the illustration. Kindly read the statement of number 16. Have you read it? Fine. For closed pipe, just now we have seen the expression of frequency. What was that? Fn equals to 2n minus 1 into V upon 4L. Here it is. 2n minus 1 into V upon 4L. Closed pipe, we take it as a first pipe, so its length I am showing by symbol L1. Okay? But in case of closed pipe, they are talking about second overtone. Second overtone. For second overtone in the previous topic, we had taken n equal to 3. Remembered? Just take n equal to 3. Why? Tell me. In case of closed pipe, what was the possible values of frequency? F1, 3F1, 5F1, 7F1. Got it? After F1, whichever higher frequency is possible, that is 3F1, is called first overtone. Correct? After that, whichever higher frequency is possible, higher than first overtone, we call it second overtone. So for second overtone, the frequency is 5f1. Frequency is 5f1. Now this is f1. So this must be 5. So just compare this with 5. 2n minus 1 equal to 5, then n will be 3. N will be 3. So remember, n equals to 3. Got it? Put n equal to 3 here, you will get f3. Put n equal to 3. 3 to the 6 minus 1, that is 5 v upon 4 L1. 5 v upon 4 L1. Give it equation number 1. Okay? In the second case, they are talking about open pipe. For open pipe, what was the expression for frequency? Fn equals to n into v upon 2L. N into v upon 2L. Remembered? N into v upon 2L. But because open pipe we right now consider as a second pipe, we just show its length by symbol L2. Fine. In case of open pipe, they are talking about third overtone. Third overtone. And for third overtone here, you should take n equal to 4. N equal to 4. Why? Which were the possible frequencies here? F1, 2f1, 3f1, 4f1, 5f1, 6f1, dash dash dash. Correct? Higher than f1, it is called first overtone. Higher than first overtone is called second overtone. Higher than second overtone is called third overtone. Higher than third overtone, it is fourth overtone, and so on. Here they are talking about third overtone, for which n equals to 4, and the frequency is 4f1. 4f1. Okay, fine. So when you write this frequency as 4f1, then this is f1. V upon 2L is f1, and when you write 4f1 means n is 4. N is 4. N equals to 4. Correct? Place n equal to 4 here. f4. Then place n equal to 4 here also. 4 into v upon 2L2. 4 into v upon 2L2. Give it equation number 2. Wait. Here in the statement they have said that second overtone in case of closed pipe and third overtone in case of open pipe are equal. So they have given indirectly f3 value equal to value of f4. Simple. What have they given? f3 equals to f4. What is f3 right now? It is 5v upon 4L1. 5v upon 4L1. What is f4? It is 4v upon 2L2. 4v upon 2L2. Correct? Now tell me, what have they asked? They have asked the ratio of lengths of closed pipe to the length of open pipe. Ratio of lengths of closed pipe and open pipe. In short, they have asked L1 upon L2. See, this wave velocity is same because you are talking about same air column in both the different pipes. Correct? So air column, the medium is same, then wave velocity has to be same. So if these two V are equal, we can get it cancelled. Come on. Find out L1 upon L2 from here. You will get L1 upon L2. 5 2s are 10, 4 4s are 16. 10 upon 16 divided by 2, you will get here 5 upon 8. 5 upon 8 is the ratio. If they are asking about proportion, the proportion is 5 is to 8. 5 is to 8. Okay, fine. Now, kindly read this statement of number 17. Have you read it? Look. In the syllabus of practicals, you will have one practical regarding resonance pipe or resonance tube. In that resonance tube, actually we are using open pipe, which is open from both the ends. But we just convert it into a closed pipe by immersing one end of that pipe into water. Say here is water medium, and we just immerse one end of that open pipe into this water medium. Now tell me, this is a pipe which is open at the top end and closed at this end. I mean at this level you can see there is a surface of water, correct, inside the pipe. So that is closed end. So one end is closed, one end is open. You can treat now this pipe as a closed pipe, for which the length is between open and closed end, that length is capital L. Okay. Now what is the benefit of such an arrangement? When you just place here some tuning fork which is vibrating with a fixed value of frequency, with the same frequency the air column also will vibrate. Okay. But if you can have here antinode, if you can here have antinode, then at the position of amplitude, don't you know, the amplitude of oscillation is maximum. If amplitude is maximum, then corresponding intensity also is maximum, because intensity is directly proportional to square of amplitude, correct. So when intensity of sound heard from here is maximum, then you can have here maximum loudness of the sound, then that particular length we want to find out. Okay, fine. So what we can do here, till we get maximum loudness, we can go on changing this length, correct. You can just take the pipe up and down, correct, till you hear maximum sound, I mean sound with maximum loudness. So till you get maximum loudness of the sound, you are supposed to adjust the length of this closed pipe. Got it? Fine. Now when resonance has taken place first time, this length we will take as L1, and second time we will take it as L2. Now let us see. For closed pipe, don't you know the frequency expression? What was it? Fn equals to 2n minus 1 into V upon 4L. 2n minus 1 into V upon 4L, correct? Now for resonance in the closed pipe, the frequency of oscillation of this branches of this tuning fork and frequency of oscillation of air particles inside must be same. That's what I am writing here. Fn must be equal to F, where Fn is frequency of oscillation of particles of air medium, F is the frequency of oscillation of branches of the tuning fork. They must be equal. When these frequencies are matching, at that time resonance is said to have taken place. Now what is Fn formula? It is 2n minus 1 into V upon 4L. 2n minus 1 into V upon 4L. This F as it is. Find out L from here. L you can just make subject of the equation. It will be 2n minus 1 into V upon 4F. 2n minus 1 into V upon 4F. Correct? At first resonance, you should take n equal to 1. First resonance takes place at the lowest possible value of frequency. Okay? Take n equal to 1. Then at that time length of the closed pipe I am taking as L1. Take n equal to 1, L equal to L1. Put it here. L equals to L1. Put n equal to 1. So 2 ones are 2 minus 1, that is 1 into V upon 4F. That is V upon 4F. Give it equation number 1. Now at the time of second resonance, see whether it is first resonance or second resonance or third resonance, whatever that may be, whatever the order of resonance may be, but every time at the time of resonance, at the top end which is open, you are going to have maximum amplitude. That's why maximum intensity. Maximum amplitude means here it must be position of antinodal point, correct? For that, what should be the new length? Because we are now changing the order of resonance. Order of resonance is now not first, it is now second resonance. Okay? Just put n equal to 2 and L equal to L2. Put n equal to 2, L equal to L2 in this formula. Come on. L equals to L2. Then put n equal to 2. Then 2 to the 4 minus 1, that is 3V upon 4F. 3V upon 4F. Correct? Look at these two right hand sides. Look. Correct? They are different. They are different. So this length also must be different. Here we have taken L1, here we are taking L2. Frequency of tuning fork is same. Frequency of tuning fork is same. And the wave velocity also remains same. But here right hand side is changing, then left hand side also must change. Lengths are changing from L1 to L2. Got it? Fine. Similarly, in the examination, suppose you are given third resonance. Suppose third resonance. You may write n equal to 3, L equal to L3. Simple. Fine. Come on. Because this length is greater, I would subtract this from this. So L2 minus L1, I am taking L2 minus L1. It would be this minus this. This minus this, it will come out V upon 2F. 3v upon 4f minus v upon 4f, that is 2v upon 4f. 2 into v upon 4f, that is v upon 2f. v upon 2f. Now this greater length they have given 31.25 centimeter, smaller length is 9.75 centimeter. Mind well, when these two lengths are taken in centimeter, this wave velocity will be obtained in centimeter per second. V as it is 2 into f. F is frequency of this tuning fork. That frequency you are given 800 hertz. This frequency is 800 hertz. Okay. Simplify. Value of wave velocity you will get 34,400 centimeter per second. But you know 100 centimeter is 1 meter. So divide this by 100 to get the value of velocity in meter per second. Divide this by 100. You will get 344 meter per second. 344 meter per second. Okay. That is the velocity of sound wave in this air column. Simple. Fine. Then we go for another theoretical article, very interesting. It is about phenomenon. It is called bits. What do you mean by bits? It's very interesting phenomenon. I am showing you what is that. Consider two tuning forks. Two tuning forks having slightly different frequency. Suppose we take first frequency as 245 hertz. Second frequency will take 240 hertz. So which are the two values? 245 and 240. What is the difference? Difference is 5 hertz. Okay. Take such two tuning forks having slightly different frequencies. Strike them with the rubber pad and hold them this way. Okay. Then first sound wave coming from this first fork, second sound wave coming from the second fork, they will superpose at this position where you are observing the phenomenon. Fine. Actually you are listening the effect. Okay. Now at this point of superposition, it will so happen you will have production of resultant wave. When two waves will superpose, they will produce resultant wave. At the point of superposition, what we experience, that intensity of sound wave, resultant intensity of the wave is changing periodically. That is increasing from 0 to maximum, decreasing from maximum to 0, again increasing from 0 to maximum, again decreasing from maximum to 0, and so on. This very phenomenon in which intensity or loudness of the sound wave goes on increasing, decreasing, increasing, decreasing periodically is only known as phenomenon of bits. We will shortly call it bits. Okay. So bits is that phenomenon. And number of times intensity of resultant wave is becoming maximum or minimum in unit time, that number is known as bit frequency. Bit frequency. Okay. Come on, what is that bits phenomenon? Let us study in detail, and we will derive the expression of bit frequency also. Fine. Look, consider this as first sound wave having frequency f1, this as second sound wave having frequency f2. You can see in the figure f1 is greater than f2. f1 is greater than f2. Why? Compared to this, here distance between two consecutive crests is smaller. Distance between two consecutive crests is called wavelength. If wavelength here it is smaller, then frequency must be higher. So f1 is greater than f2. When such two waves having same amplitude and having slightly different frequencies, when they superpose on each other, the resultant wave is like this. Resultant wave is like this. Fine. This is the resultant wave, okay, in which the frequency is found to be mean value of f1 and f2. Mean value of f1 and f2 means summation divided by 2. Summation divided by 2. f1 plus f2 divided by 2. Okay, fine. Now the two sound waves which are superposing on each other, let us express them mathematically. y1 equals to a sin omega 1 into t, and second wave y equals to a sin omega into t. But for first wave, here we will write y1, here we will write omega 1. For second wave, here we will write y2, and here we will write omega 2. Wait, have you remembered expression of wave equation? What was that? Y equals to a sin omega t minus kx. Remembered? But the point of superposition where the two waves superpose, we just take it at the origin. And if you take it at the origin, then for origin x coordinate is 0. So in the formula y equals to a sin omega t minus kx, when you write x equal to 0, because you are observing the phenomenon locally, put x equal to 0, you will get y equals to a sin omega t, correct? For first wave, you write here y1, here you write omega 1. For second wave, here you write y2, here you write omega 2, correct? But tell me, what is omega 1? It is 2 pi f1, correct? What is omega 2? 2 pi f2. Where these frequencies f1 and f2, we are just taking very close to each other, such that difference between them is very small, okay? Nearly equal frequencies, fine. Now, what will be the resultant displacement? According to principle of superposition, it should be y1 plus y2. Y equals to y1 plus y2. That is this plus this. So, it is this plus this. But when you take this plus this, a can be taken as common. Come on, inside the bracket, sine of 2 pi f1t plus sine of 2 pi f2t. Don't you know from trigonometry? Sine a plus sine b. Sine a plus sine b. Sine plus sine, remember the formula, 2 sine cos. Addition divided by 2, subtraction divided by 2. Sine plus sine equals to 2 sine cos. Sine plus sine equals to 2 sine cos. Addition divided by 2, subtraction divided by 2. With sine, it should be addition upon 2. Come on, this plus this upon 2. You can take 2 pi t common. And addition upon 2, meaning that by f1 plus f2 upon 2. F1 plus f2 upon 2. Into cos. Come on, subtraction divided by 2. When you take this 2 in subtraction, then this minus this, then 2 pi t can be taken common. 2 pi t taken common, subtraction divided by 2. So, f1 minus f2 upon 2. F1 minus f2 upon 2. Correct? I repeat. This a as it is, sine plus sine. How much it is? 2 sine cos. Addition divided by 2, subtraction divided by 2. Simple. Now, let me rearrange the terms on right hand side properly, okay? I just rearrange it. 2 I am writing first, then I am writing a, then I am writing cos, and then I am writing sine. 2a cos into sine. 2a cos into sine. Any problem? With cos it is 2 pi into f1 minus f2 upon 2 into t. Same term I have written here. And with sine it is 2 pi into f1 plus f2 upon 2 into t. With sine it is 2 pi into f1 plus f2 upon 2 into t. Correct? Fine. Now, with a sine function in the standard format, you can see the coefficient of time will give you angular frequency. And if you look here, then coefficient of 2 pi t, it will give you frequency. Coefficient of 2 pi t will give you frequency. Coefficient of 2 pi t, it will give you frequency. So, this is nothing but frequency of resultant oscillation or frequency of resultant wave. Frequency of resultant wave is f1 plus f2 upon 2. F1 plus f2 upon 2. Right? And in this standard format, you can see the coefficient of sine function gives you amplitude. Come on, this is amplitude of first wave, this is amplitude of second wave. No doubt we had taken these two amplitudes to be equal. But similarly here, coefficient of sine function means this much part. This entire part will give you amplitude of resultant wave. Amplitude of resultant wave. Amplitude of resultant wave, let it be a dash, which is 2a cos of 2 pi into f1 minus f2 upon 2 into t. 2a cos of 2 pi into f1 minus f2 upon 2 into t. Correct? This will give you a dash, that is amplitude of resultant wave. Amplitude of resultant wave is this much. Fine. Now you can see with time this amplitude will change periodically according to this cosine function. According to this cosine function, I am showing you. If it is changing according to cosine function, again what is the frequency of oscillation of amplitude value? Come on, frequency of oscillation you should find out in this angle by finding out the coefficient of 2 pi t. Coefficient of 2 pi t, how much it is? f1 minus f2 upon 2. f1 minus f2 upon 2. This will give you frequency of amplitude of resonant wave. Frequency of amplitude of resonant wave. I repeat. This is simply amplitude of resonant wave, let it be a dash, but with cosine function inside this angle, whatever is the coefficient of 2 pi t, that will give you frequency, and it is f1 minus f2 upon 2, f1 minus f2 upon 2, correct? Now let us find out periodic time. Don't you know periodic time is nothing but 1 upon frequency, reciprocal of frequency is called periodic time. So 1 upon this frequency, which is f1 minus f2 upon 2. Denominator will become numerator, so 2 will go in the numerator. 2 upon f1 minus f2, 2 upon f1 minus f2. Wait, tell me, from this formula, can you make out that this amplitude is going to change periodically according to cosine function? So why don't you plot a graph of a dash versus t? This is amplitude of resonant wave, this is time. But it will be the graph of cosine function, because in this formula there is a cosine function. Don't you know the graph of cosine function? It is like this. Starting from maximum, the graph is this. Fine. Now this is one periodic time, that is capital T. Now consider the time interval after 0 up to capital T. After 0 up to capital T. After 0 means 0 you should not consider. And up to capital T, capital T you must consider. In this much time interval, now you can see from this graph, this amplitude here it becomes maximum, here also it becomes maximum. But at these two very instants, come on, that amplitude value becomes 0. So up to capital T time, this amplitude of resonant wave becoming maximum 2 times and 0 also 2 times. Now don't you know, intensity of wave is directly proportional to square of its amplitude. Directly proportional to square of its amplitude. The moment amplitude will become maximum, intensity also will become maximum. The moment this amplitude will become 0, this intensity also will become 0. So in this much time, intensity of resonant wave will become, come on, 2 times maximum, 2 times 0. 2 times maximum, 2 times 0. Same thing I am writing here. In capital T time, look, in capital T time, intensity, number of times intensity becomes maximum or minimum. Number of times intensity becomes maximum or minimum, it is found to be 2. 2 time becoming maximum, 2 time becoming 0. In this much time, if intensity of resonant wave becomes maximum or minimum 2 times, then in unit time, how many number of times will it become maximum or minimum? Let us find out. In this much time, this many times, then in unit time, how many times? This into this upon this, it will be 2 upon t. Say 2 upon t. This 2 upon t will give you number of times intensity of resonant wave becomes maximum or minimum in unit time. That very number only I told you initially, it is called bit frequency. What is it called? Bit frequency. So I am writing here bit frequency. Expression of bit frequency is 2 upon t. But can't you find out 2 upon t from here? 2 upon t, transfer this. 2 upon t, it will be f1 minus f2. Come on, 2 upon t will be f1 minus f2. 2 upon t is nothing but f1 minus f2. That is, in short, in words you can say greater frequency minus smaller frequency. If f1 is greater than f2, you can take f1 minus f2. If f2 is greater than f1, then you can take f2 minus f1. Got it? So this is giving you that number of times the intensity of resonant wave will become maximum or minimum in unit time. That very number is known as bit frequency. And this phenomenon in which intensity of resonant wave becomes maximum, minimum, maximum, minimum, means it is going on changing periodically. That very phenomenon is called bits. When two waves having same amplitude but with slightly different frequencies superpose on each other, the phenomenon of intensity of resonant wave becoming maximum and minimum periodically is known as bits, and number of times intensity of resonant wave becoming maximum or minimum in unit time is called bit frequency. I repeat both the definitions. When two waves having same amplitude but slightly different frequencies superpose on each other, the phenomenon of intensity of resultant wave changing periodically at the point of superposition is called bits, and number of times intensity of resonant wave becoming maximum or minimum in unit time is called bit frequency. Last time, when two waves having same amplitude but slightly different frequencies superpose on each other, then phenomenon of amplitude or intensity of resonant wave becoming maximum minimum, that is changing periodically with time, is called bits, and number of times intensity of resonant wave becoming maximum or minimum in unit time is called bit frequency. Okay. If you are talking about phenomenon of bits in case of sound waves, then practically we find that if the bit frequency value is more than 7, then no doubt phenomenon of bits will take place, but you cannot experience the phenomenon of bits clearly using your human ears, you cannot clearly experience. In order to experience the phenomenon of bits in case of sound waves clearly, the maximum value of bit frequency should be 7 hertz, it should not be more than that, it should not be more than that. That's what I am writing here. Look, maximum value of bit frequency. Bit frequency is nothing but difference of frequencies. Maximum value of this difference should be 7 hertz. It should not be more than 7 hertz. If the bit frequency is more than 7 hertz, phenomenon of bits will take place, but we cannot experience. If the difference is 7 hertz or less than that, then we can clearly hear the sound is becoming with maximum intensity, the loudness is maximum, the loudness becomes 0, becomes maximum, becomes 0, becomes maximum, becomes 0, like that. The periodical changes in the amplitude and hence the intensity or loudness we can experience, okay, we can hear accordingly, and then we can say that phenomenon of bits is experienced clearly, okay, fine. Now, based upon this theory of bits, there is one very good example, number 18. Read the statement of example number 18. Have read it? Fine. Suppose two given tuning forks are A and B, and suppose we do not apply wax on tuning fork A. They have said in the statement, the fork on which wax is not applied has frequency 512 hertz. Here it is, 512 hertz. If you are applying wax on B, means you are not applying wax on A. Because wax is not applied on A, its frequency they have given in the statement 512 hertz. So, I am writing here FA equals to 512 hertz, correct. Now, initially before applying wax on the fork B, the bit frequency between A and B, they have given bit frequency value directly is not given. They have said that 20 bits are heard per 8 seconds. 20 bits are heard per 8 seconds. If 20 bits are heard per 8 seconds, what is the number of bits in 1 second? 20 upon 8, it will be 2.5 hertz, correct? But number of bits in 1 second, what is it called? Bit frequency. Bit frequency means what? Difference of frequencies. So, you can say it is FA minus FB or FB minus FA. Difference means what? You can take FA minus FB or FB minus FA. That bit frequency or difference of frequencies must be 2.5 hertz. I repeat, what is bit frequency? Tell me. Number of bits per 1 second. What have they given? 20 bits are heard per 8 seconds. So, when you take 20 upon 8, you will get number of bits in 1 second, which is called bit frequency. It will come out to be 2.5 hertz. And bit frequency means difference of frequencies. You may take two ways, FA minus FB or FB minus FA. When before applying wax on B, I am writing here, before applying wax on B, correct? Fine. Now tell me, difference is this much, difference is this much. What does it mean? That you find out those two values which has difference of 2.5 with this value. How to find out such two values? Very simple here. You just add 2.5 and you subtract 2.5. Add 2.5, subtract 2.5. When you add 2.5 here, how much it will be? 514.5 hertz, correct? And if you subtract 2.5 from this, it will be 509.5 hertz. Got it? Fine. So before applying wax on the pronges of tuning fork B, its frequency could be 514.5 hertz or it can be 509.5 hertz also. Now tell me, if you apply wax on tuning fork B, its pronges would become heavy. When you put some wax on the pronges, naturally pronges would become heavy. And when the mass increases, periodic time of oscillation increases. When periodic time of oscillation is increasing, frequency would decrease because frequency is reciprocal of periodic time. I repeat, when you apply wax on the pronges would become heavy. When mass increases, then the periodic time also will increase. When periodic time is increasing, then frequency will decrease. Fine. So after applying wax on the pronges of tuning fork B, we know its frequency is going to decrease. But after that, it so happens, they have given in the statement that now the number of bits heard between A and B in 8 seconds, it is 32 now. 32 bits are heard in 8 seconds. 32 bits are heard in 8 seconds. So what is the number of bits in 1 second? 32 upon 8, it will be 4 hertz. And now, because you have applied wax on the tuning fork B, its frequency is lesser than FB, lesser than FB. Let it be FB dash, let it be FB dash, correct? For tuning fork A, we are not making any change, so its frequency will remain same, FA. But now the difference is 4 hertz. Difference means what? You can take FA minus FB dash or FB dash minus FA, correct? Now in short, you just find out such two values which have difference of 4 with 512. Find out such two values which have difference of 4 with 512. How to find out such two values? Very simple here. Add 4 and subtract 4. That's all. 512 plus 4. How much it is? 516. Correct? And if you subtract 4 from this, you will get 508 hertz. But I say this value is not possible. That's why I am putting cancellation mark here. Why this value is cancelled? Why it is not possible? By putting wax on B, its frequency will decrease. Its frequency will decrease. So it should be smaller than this. It should be smaller than this. Correct? But tell me, is this value, is it smaller than this? No, this value is greater than this. Correct? So this is not possible. Correct? So after applying wax, the frequency of tuning for B, if this is the value not possible, then this value must be possible. What is that value? 508 hertz. But when after applying wax, that's why I am putting symbol FB dash, correct? And before applying wax, its frequency is such that it has difference of 2.5, with this, correct? And such two values are these and this, correct? So before applying wax on B, its frequency could be 514 hertz also, it could be 509.5 hertz also. But after applying wax, what will happen? Frequency will decrease, but it will decrease to that value such that that value should have difference of 4 hertz, difference of 4 hertz with 512, and that value is none but 508 hertz. In short, before applying wax on tuning fork B, its frequency can be this or this. That's what I am writing here. Can be 514.5 hertz or 509.5 hertz before applying wax on B. And after applying wax, it will decrease to this value such that this value 508 has difference of 4 hertz with 512 hertz. Got it? In textbook, before applying wax, they have taken this value into consideration. No doubt it is correct answer. But along with this correct answer, this is also one more correct answer. This is also very much possible. They have not mentioned that thing. Okay. So these two are the possible values of frequency for tuning for B before applying wax, and this is the frequency of tuning for B after applying wax. Got it? Similarly, they may just change the statement. Suppose you rub the pronges of a fork. If you rub out the pronges of a fork little bit, then mass will decrease. When you rub the sponges, naturally mass will decrease. When mass will decrease, then periodic time will also decrease. When periodic time will decrease, frequency will increase. Don't try to remember both at a time. At present, you simply remember when you increase the mass, no doubt by putting the wax, when you increase the mass, periodic time will increase and hence frequency will decrease. So, you simply remember one thing, when the sponges become heavy, frequency decreases. When the sponges become heavy, frequency decreases. Please remember this, okay.